Okay, so today we're going to do an extension lesson for the equilibrium computations, the equilibrium systems. We call that the electrolyte effects because in equilibrium systems, if you add substances in there, it will affect the state of the equilibrium system. We call that the Le Chatelier principle. However, that must have been previously discussed in your general chemistry subjects. Okay, so today we're going to focus deeply into the effects of ions in an equilibrium system. Okay, so let's have this problem. The KSP for AgBr silver bromide is 5.4 times 10 raised to negative 3 at 25 degrees Celsius. We have to calculate the molar solubility of AgBr in 0.05 molar silver nitrate solution at 25 degrees Celsius. Okay, so as you can see, what will happen is that this salt, this silver bromide, is a precipitate. However, this will dissociate a little bit to produce silver ions and bromide ions. Okay, so let's disregard this first. Okay, let's disregard that first. Okay, what we're going to do is that given the KSP, we're going to look for the solubility of silver bromide in pure water. Okay, in water only. So to do that, we're going to use an ice table. Ice. Okay. So remember, for solids, we are not going to write anything on the ice table part because that's not needed anyway. So initially, if our silver bromide is in water solution, the concentration of silver is 0 as well as bromine. That's also 0. And according to reaction quotient, the direction of reaction is going to the side without concentrations. Okay, so that means the change in the concentration for silver is positive x because the coefficient for silver is 1, and the same is also true for bromide. So at equilibrium, 0 plus x is x, this one is x again, and then we write the KSP expression, which is the concentration of silver in equilibrium times the concentration of bromine in the equilibrium. And we're going to substitute the equilibrium concentrations, which is x. So that is KSP equals x times x. So to solve for the molar solubility, we're just going to solve for the value of x. So since our KSP is equals to x squared, x is just the square root of our KSP, which is, allow me to solve for that first. The solubility, the molar solubility of silver bromide in pure water is around 7.348. Let's round it off. 7.35 times 10 raised to negative 7 molar. So this is the molar solubility in water. Okay. So how about the second part of the problem? It tells us to calculate the molar solubility of silver bromide in silver nitrate solution. Okay, so this is our second condition. We're going to solve for the x, or the molar solubility in a solution with 0.05 molar Ag silver nitrate. Okay, so still we're going to use the ice table as always. Okay, so then ice table. Okay, so for solids we're not going to write anything at all. Okay, so looking at the problem, the solution already contains silver ions. Where does that came from? Okay, that came from this part. Our 0.05 molar silver nitrate solution will dissociate into silver ions and nitrite ions. So okay, so what will happen is that since we have silver nitrate in the solution already, that will dissociate into silver and nitrate ions. So we have 0.05 concentration for that. So stoichiometrically, this is also 0.05 molar. Same goes for this one as well. Okay, so that means the initial concentration for the silver ion in our system is already 0.05 molar. We don't have any for bromine, okay, or the bromide ion, so that is still 0. And since we do not have any bromide ion concentration, the system will shift to the right side, to the side without ions. Okay, so that that means the reaction is going to the product side. Okay, so for change, this is positive X for the silver, positive X for bromide ion. Okay, then for equilibrium, that is just 0.05 plus X. This is X. Then we proceed solving for X. Okay, so X is still the molar solubility. Okay, because the 0.05 here is already present in the solution. That doesn't represent the solubility of our precipitate. Okay, we're just going to look for the value of X. So let's write the KSP expression. So KSP, in this case, is the concentration of silver ion in the solution at equilibrium times that of the bromide. That means this is KSP equals 0.05 plus X times X. Okay, what can you notice? We'll be dealing with quadratic equations here. So let's simplify this anyway. Let's distribute X. That is KSP equals 0.05X plus X squared. Then we're going to transpose KSP on the right side to linearize our equation. So that is 0 equals X squared plus 0.05X minus KSP, or X squared plus 0.05X minus 5.4 times 10 raised to negative 13. So what's next? We're going to solve for X. Okay, so solving for X, we will get two roots. Okay, so allow me to solve for that using the calculator. If you don't have a calculator that's capable of solving quadratic equations, you can use online calculators anyway. Or you may use the quadratic equation if you want. Okay. So the first root I have here is 1.08 times 10 raised to negative 11. Second root is negative 0.05. Okay. Of the two roots I solved, which of the following is the correct answer? Okay, we will go for the first root because that is the root that is making sense, because there are no negative concentrations. Remember that. No negative concentrations, so we're only getting the positive root. Okay, so that means this is the molar solubility of silver bromide in 0.05 molar silver nitrate solution. That's equal to 1.08 times 10 raised to negative 11 molar. Okay, so what can we observe? If your precipitate is dissolved in water, the solubility is this: 7.35 times 10 raised to negative 7. If your precipitate is dissolved into a solution with common ion, in this case that's silver. Where did silver came from? Okay, it came from the silver nitrate previously mentioned. So if your precipitate is dissolved in a solution with common ion, the solubility is lowered down to 1.08 times 10 raised to negative 11 molar. This phenomena, or this effect, is called the common ion effect. Okay, so this is the common ion effect. Basically, the summary is that when you add common ions in your equilibrium system, the solubility, the molar solubility of your substances generally decreases. Okay, adding common ions decrease solubility. Okay, so that's the idea for common ion effect.